Okay, so let's start the class. So hopefully everything is set up now. All right, so second lecture in CME 213. All right, so we published homework 1. Okay, so it's so you get the files by going to the GitHub class webpage. Okay. So you don't really have to use Gradescope at this point, but we set up the homework on Gradescope, so you can track the deadline on Gradescope and make sure you submit ahead of time. But okay, so it's prerequisite homework, sort of covering basics of C++, like kind of a refresher. C++ derived classes. Like polymorphism, when you call a function, on a base class or derived class, and it has a different behavior. So the so-called standard library, so the standard template library, which provides a lot of functionalities that are very useful for C++ programming, and also covers some aspects of testing. So as I mentioned, when you write code, you want to learn some good practices, write small chunks of code, then you should be able to test that this code is behaving properly, like try different inputs, look at the outputs, can investigate and verify that's working correctly. And then once you have this working, then you can sort of move on to the next small snippets of code. Okay, so so to submit the homework, okay, so we went through that. So it's actually separate from Gradescope. So actually, what we recommend for this homework is, well, to a large extent, you can run on your own computer. It's pretty standard, just C++. But we'll be sort of testing your file on Rice. So maybe at some point you just want to copy your files over to Rice and run them there, compile and run to make sure it's correct. So the script needs to be run from the kernel machine. I think so, unless I'm mistaken, Rice and kernel is basically the same directory, right?
Both.
Right. So there's no actually copying between Rice and kernel. Right. Okay. Right. So it's a shared file system. So the files you have on Rice are essentially also on kernel. But if they're on your laptop, then obviously you need to copy them to kernel. So the script, though, you have to run this on kernel just to make sure that it's sort of the same Python installation as on Rice. So you run this Python script, so the instructions are in the homework, and then this copies the files over to the staff, instructors of the class, and then you can use that for grading. Okay? All right. So any questions on this? Deadline is Friday. Okay. Right. So today, sort of short introduction on parallel computing. So a little bit of background on parallel computing, is a general discussion, and then we'll finish with well, I'll discuss a little bit the basic shared memory parallel computer, what they look like and so on. And then at the end, I'll talk a little bit about C++ threads, and I have a little exercise, although we kind of may run out of time for that, so we'll see. But if you brought your computer, then you'll get 5 minutes to kind of do a little bit of exercise, programming exercise at the end of the lecture. So generally speaking, if you can bring your laptop to class, we won't have exercise every lecture, but every now and then, especially once the Google Cloud is sort of set up, then you can just connect to your Google Cloud virtual machine, and kind of do the homework there or the exercise. So good idea to bring your laptop to class. Okay, so it used to be that running sequential codes was sort of sufficient for most purposes, but essentially, as soon as you go to any type of non-trivial computing, once you start crunching a lot of numbers, then essentially you need to go parallel. So going parallel is a pretty complex process. So fortunately, using OpenMP, and if you have like a C, C++ code, it's pretty straightforward. But there is definitely a big jump in complexity. But as soon as you do some non-trivial calculation, this is basically a requirement. So just a little bit of a sort of historical background on this. Programming parallel processors is very complicated. It's a pretty obvious way to run very large-scale calculation. And if you look at whatever Amazon, Google, obviously they have to go parallel. But for the average user, it's a little bit less obvious. And for example, you could say, well, if you have 4 processors, you can do your calculation at a certain speed. But if you have a single processor that's 4 times faster, you achieve the same objective. So for many purposes, it feels that having just a sequential code that simply runs on a faster processor, is the way to go. And so for many years, that was the logic, because obviously programming sequential is much simpler than parallel. So nobody wanted to write parallel code, so the vendors were simply cranking out faster processors, and everybody was happy. And then so there was this Gordon Moore law that the number of transistors should double, and essentially the clock speed was pretty much increasing at the same rate. And so you could do more calculation faster and faster, and so there was no need to go parallel. But this came to to an end. So now it's actually some time ago, maybe you can say in 2000s or somewhere along those lines, 2005. So almost 10, 15 years ago. So you have various plots and various ways to show this. So there's basically a number of physical limitations. Okay, so for example, if you look at this plot, so in black you have the number of cores on a processor. In red, the power consumed by your processor. Here, this is the frequency at which your processor is operating. Okay, and here you have the single thread performance and the transistors, number of transistors at the top. So you can read a number of things on this plot. So first of all, for example, looking at the number of cores, everything was sequential up to 2005. And so actually, if you wanted to do, parallel computing, goes back a while. But if you wanted to do parallel computing in the good old days, I was born here. I was alive during quite a bit of that time, and I did do that. So when you wanted to do parallel computing, you basically had to run on multiple computers, right? There was no such thing as running in parallel on a single processor. That was kind of a contradiction. There was only one core on each processor. Okay. And okay, so that means that the process was actually rather complicated, but that was this increase in performance. So to some extent, unless you were a hardcore scientist, really, into computing and so on, people really didn't care too much. But then, so essentially you had this frequency increase, and you would, I remember in that time when you were buying a processor, they had all these fancy names, but at the end of the day, you would just look at the frequency, and that was essentially how good your processor is, okay? And then at some point in 2005, frequency stalled, and so the single thread performance, kept increasing, and the increase, I didn't do the slopes here, but definitely there was a fast increase here, and then a slower increase here. So the performance is a combination of two things, right? It's a combination of the frequency, essentially how fast, basically to some extent, every operation on the processor happens during a cycle, like things are synchronized, because otherwise it would be just crazy to manage the processor. So everything is on this clock with the cycle, given by the frequency. So if you increase frequency, it's like just going faster. Okay? And so this is one reason why you get more performance, but also, you know, if you have more transistors, you can do more things, you can do a lot more optimizations. And so even if the frequency is flat, it's still possible to get improvements in performance, but this is a lot harder. So here, for example, if you look at the rate of improvement in single FET performance, it goes down quite a bit. But if you look at transistors, you know, it keeps going up, actually following this Moore's law, more or less. And it goes way faster than the single FET performance. Here they sort of, you know, a little bit parallel, but definitely over there they diverge. And of course the divergence is because simply you're cranking more and more cores, okay? And so, you know, now it's well, you know, these might be very high-end processors, but, you know, any processor nowadays may have 4 cores, but it can go up to 6 or even 12, okay? So, and then there are some more exotic processors who's really a lot. And then of course, and if you look at GPUs, so it's multiplexer on GPUs, they really have even more cores. So this is how you can get, you know, performance, basically unable to increase frequency, unable to some extent to increase single FET performance. So now you have to rely on being parallel at the level of the processor itself. And so essentially this gave rise to 2 types of parallel computing. The shared memory, which is basically using many cores on a processor, sort of to simplify the discussion, and distributed, which means, well, putting computers together with a fast network, which is sort of what was happening in those years to, you know, to crank more flops. Okay. And so essentially the reason why, you know, the frequency stop increasing is for, you know, essentially physical reasons. So, you know, I don't know all the details of the physics and so on, but essentially, you know, to go faster, you have to make things smaller. Okay, that's, you know, roughly the idea. You can pack more transistors on your die, but also you can just make things faster. But there's a limit to how small wires can be. Okay, so maybe nowadays the technology might be 10 nanometer, which, you know, maybe even 10 years ago would seem impossible. But you know, even if you keep pushing the impossible, you know, if you're down to less than 1 atom, you know, definitely there's something wrong with your computer. You know? So there's definitely a limit to how small, you know, you can be. So for example, for transistor, you have problem of leakage. That is, you know, you need to be on-off, but when you're very, very small, you know, the difference between on and off becomes smaller. Like there's current that is going through even when you're supposedly off. Okay? And then the last 2 points are sort of critical for sort of different reasons, this power consumption. So first of all, the processor gets really hot, okay? And there's a lot of strategies nowadays to mitigate this, but basically, you know, as you make things smaller and you want to run faster, things get hot, and the die is just a certain volume. Okay, it's pretty flat, but it's a volume, and even if you blow cold air and so on top of it, you know, like the core of the die really cannot cool all that fast. It's really just diffusion. There's just a limit to how much heat you can generate inside the die. Okay, and so that puts a stringent limit on your frequency and how fast you can go. And then moreover, so this is slightly different issue, but when you build a supercomputer, well, you know, you can just keep adding cores to your computer. You know, if you're Google or, you know, or the government, you know, with unlimited taxpayer money, you know, you can just keep cranking these cores. But, you know, it does take more and more power. It's not that easy to bring a lot of electricity into a small building, and it costs just a tremendous amount of money. And so actually for the large supercomputing facilities, the power consumption and simply just like the amount of electricity you have to feed into the computer becomes a really big issue. Okay, and in many cases, you know, it's more efficient to, for example, have 10 cores that are somewhat slow than, say, you know, 2 or 4 that are really fast. Because, you know, to get this extra 10% faster, you may need like twice the amount of energy or something like this. Okay, and then finally, and so this is also a very important thing that, you know, you will come back to this over and over again, this question of memory, which is that, again, it's sort of has to do with the physics of things and so on. But if you want to just, if you think about computing, performing operations on variables, well, that can be made extremely fast because essentially, you can be on your tiny process, on your tiny transistor. You have a little bit of memory, with your registers where you can store your variables, and you feed this into a pipeline, like a bunch of transistors and so on that do the calculation, and then you output the result in some other register. Everything is super local, okay, and you can really optimize this. And more importantly, you can multiply these computing units, a lot. And so really flop is very easy. But memory access is very challenging, okay? Because if you think about memory, okay, well, realistically, you may need 8, 16, 32 gigabyte of memory or more on each node. So that's just a lot of data. So as a result, this data sort of needs to be far from where the computing is happening. And by this I mean there's a lot of wires, and they have a certain distance. And this distance, may be just a couple of centimeters, but for an electron to travel that distance, it's a lot, okay? And there's a lot of logic and so on that needs to go with that. And so the memory access time is actually, so this is also a very sequential process very often. I mean, you can make your memory parallel, but also that is very difficult. So memory access time is also a big problem. And improving the speed of memory is something that, there are very strict restrictions on what you can do there. So the flops you can multiply, the memory you can also sort of multiply by putting more and more wires in parallel. So anyways, so in both cases the solution is to just do more stuff at the same time concurrently, so you go parallel. So of course for hardware inventors that's relatively simple, so to speak. Just multiply the number of cores, put more wires for the memory and so on. But for the programmer, this is significantly more complicated because we all, as humans, think sequentially. It's very hard to think, in parallel. I mean, we can think about independent things happening at the same time, but as soon as we start saying, well, actually these things are happening at the same time, but there are certain dependencies between them, then it becomes a lot more difficult. Okay. So, and so again, a little bit of preview of what's coming up ahead. So you basically have two types of multi-core processors. So you have the sort of the regular, like Intel, or AMD, processors with multiple cores. So typically, like I said, you have 4 or 6 cores, and this is for the sort of general purpose applications. So you have to be able to do anything from running, web browser, your document processing, to doing maybe scientific computing, if you're into that. So you're going to design, relatively few cores, but very advanced, okay, very fast, lots of optimization, huge cache. So, general purpose, lots of, you're being very clever. Well, I don't know if this guy's clever, but anyway, you can be very fast. All right, and then at the other sort of end, is GPUs or accelerators, and there's been sort of many variants on that. And for these applications, we're saying, well, okay, I really just want to do, a large number of matrix multiplications or simple, arithmetic, and I just have a billion of those sort of simple operations to do in parallel. So I don't need all this complexity of cache and very clever hardware. What I want is just a lot of units to do additions, multiplications, and so on. Okay, so this is a different design. You have all these not so clever cores, but like the ants, you really have thousands and thousands of them. So you can carry very heavy workload, but each unit is super basic. And though for certain type of calculation, for example, linear algebra or very regular operations, or like deep learning, actually this is a good this is a good fit because you have relatively well-structured, well-understood regular operations, but you just have to do that super fast. So you have many cores, very simple, but because you have so many, then you can crank a lot of operations, and this is a model for GPU computing. Okay, so this is sort of a little bit of a preview of what's coming up this quarter. So there's a lot of these plots online and so on. So you can look it up. So for example, this is again coming back to I have just a couple more plots on this. So actually, this is a different type of plot with just looking at Intel microprocessors, but it's basically the same thing we're seeing with frequency here. This is the power. These are the cores. At the top, you have the transistor. And on the right, you have the GPUs, okay, NVIDIA GPUs. And so pretty much the same thing, okay. The frequency is about, it's plateaued. The number of transistors, so I need to look at the units here. So it's kind of comparable, but it's, well, it's on the log scale, so it's actually, really quite a bit more. And then the number of processing units is significantly larger. So it's almost, on recent GPUs, it's more like, well, it depends how you count, but it's more like in the thousands of cores or threads that can run concurrently. So they're very basic threads, but you really have, a very, very large number of them. Okay, and then another look at a different piece of data here, which is, so this is something very important when doing computation, and this is this memory wall. And so this has to do with essentially, so it's not too bad, because obviously vendors are trying to mitigate this, but it has to do with the discrepancy between how fast the memory is versus how fast the computing is. So you can make the memory parallel. Okay, you can make the memory parallel. I mean, it's not that simple, but roughly speaking, you can, even if you have basically slow wires, if you put more of them, you can improve the bandwidth to memory. It's not super simple, but it's still possible, so you can mitigate this issue. But for example, so here you have the memory bandwidth are these yellow guys, and then the computing. Let's say this is the well, you have the vector and scalar performance. So let's just look at the vector here, on top. So this is a peak performance as well here, peak memory bandwidth. So they're, both increasing, although the peak performance, which is basically just doing flops without memory access to some extent, goes faster than the memory. And so the quantity that's more interesting to look at are these gray symbols. Actually, I'm just going to stand over there to see exactly what you guys can see in this spot. I don't have my glasses, so I can't see anything. All right, so it is small, but you can still see it a little bit. So anyway, it's just a trend, really. So these guys here, these circles, so this is a very important quantity. It's called the compute memory ratio. And so basically, this is looking at, let's say you read a word from memory. Essentially, so let's say you just keep reading words from memory at the highest bandwidth as fast as you can. Well, pretty much how many operations, a floating point operation, can you do with this word before the next one comes in? Okay, so it's basically looking at the balance where you're doing enough flops that the rate at which you're doing flops, or the time it takes to do all these flops, is equal to the time it takes to do memory transfers. Okay, and the reason why this is important is, let's say that you're doing a calculation. Okay, so you have this ratio. Well, you want to know, are you limited by how fast you're reading from memory or how fast you're doing flops? Okay, so if you have more, so you need more memory than this ratio, then essentially the computing units are going to be idle. Okay, because they can be faster, and you're just waiting on the memory bandwidth. So now it doesn't matter how fast the computing is, you just need to look at your memory, and vice versa. Okay, if your computing is the one that dominates, then it doesn't matter, how fast your memory is. You need to optimize your flops, which is not that easy. But in most applications, you're actually limited by memory. Okay, so So the computing units are actually idle. Okay, that's something that is very maybe non-intuitive, because when you look at the calculation, you naturally think, well, how many operations am I doing? And then you're going to compare algorithms based on, oh, I'm doing more flops over here, doing less flops over there. But actually, in many cases, what matters is just how much data you're reading from memory, because that is what sort of determines the speed of your calculation. Okay, like how fast essentially the flops are sort of super fast compared to the reads. And so this compute to memory ratio is gigaops per second. And so this is basically how many ops you have to do per word read from memory. And so it keeps essentially going up. So again, vendors are trying to mitigate this, because essentially the higher this number is, just the harder it is to write applications. Or in practice, it means that there are fewer and fewer applications that can really reach peak performance. Like most applications at some point become just dominated by memory transfers, and the computing units are going to be idle, and you can wasting all your technology. And so if you look at NVIDIA GPUs, the number is actually pretty high. So it's this number of floating point operation per essentially word read from memory, or per gigabyte. So you have to, multiply by 4 actually to get the actual number. So you see the floor is 4 bytes. So you're in the you're typically in the 10 to 40 range. So it's actually a lot of operations per word read from memory. For example, if you just do a matrix vector multiply with a sparse matrix or dense matrix, essentially you're reading an entry from memory, then doing the multiplications and just moving on. So you're doing very, very few flops per word read from memory. So it actually, you're completely limited by essentially how long it takes to read the matrix entries from memory to your registers, and that's pretty much it. Okay, everything else is kind of trivial. Okay, the flops are actually kind of trivial. So for example, when looking at the, there was somebody who was asking about what's so complicated about matrix multiplication that this is the final project. Well, here's what's complicated. If you're not paying attention to this memory business, when you do a matrix multiplication, you're going to be, that's n cube, operations. And if you're not careful and you're doing n cube reads, okay, at just a peak bandwidth, then this is going to be extremely slow. Okay. And so the question is, how can you reorder your algorithm so that you reduce the amount of data transfers? Okay, and so this is not trivial, but to some extent, so obviously the minimum is n squared, because you need to read your matrix entries, at least once. But between n squared and n cubed, there's a huge jump. So if you reorder your algorithm, you can be sort of very close to n squared. In fact, if you do your if you reorganize your matrix multiplication correctly, you become limited by computation rather than memory transfers. Okay, but you've got to beat that ratio here. Okay, so there's a very nice thesis that was, where I got some of these plots from, and a lot of discussion. So you're welcome to kind of look at this. Okay, so now parallel computing is nowadays sort of everywhere. So it's present in your smartphones and so on. Up to the very large supercomputers. So like I said, it's present in many forms. So on the left, you have the Intel, Ice Lake 10 nanometer architecture, and kind of a representation of one of their processors. So it's a 4-core. So again, relatively big cores, very, very fast, relatively high frequency, and lots of logic, lots of memory, lots of cache, a huge memory controller, and so on. So lots of optimizations. And here you have the NVIDIA Turing architecture. And so you actually cannot even see that. But each little thing here is actually well, I'm not sure exactly the number, but it's on the order of 32 cores. So, I haven't counted here, but it's definitely the thousands of cores. But each core is super, super simple. So that's why you can occupy, very little die space, and there's very little memory. So optimizing code for this machine is very, very complicated. But if you use all the cores, then you're golden and you can go very fast. And also this processor, for example, has a bunch of units that are dedicated to matrix-matrix multiplication, which is useful for deep learning. Okay, and then you move on to different types of architectures. So if you want to go more parallel, so this is the type of machine that scientists tend to use. So it looks like a mess, but it's actually very high-end hardware. Well, the point of this is two things. First of all, you have a lot of processors, okay, and each need to come with their motherboard, memory, and so on. So first of all, you have a design that's very, very compact, okay, like compared to a regular desktop computer. Everything is compressed, into a tiny volume, so that you can pack up, a ton of these boards, racks. A ton of these boards inside, each one of these racks, and then you just, keep going with these racks. So very, very compact, very high density, means that the cooling is also very, very difficult. Okay, so you need to blow air around this. So typically there is some type of enclosure and so on, so that you can push air from one end and then draw air from the other end and so on, and have a huge flow. There's typically it's cold water chilled, so meaning that there's some sort of something that looks like a radiator where you have the hot air going through, and then there's some pipes with some cold water to cool the whole thing, and then you have cool water coming out that you can redirect back to the computer and so on. So it's a very complicated system. So there's that. And then you have all these wires, and basically all these wires and a bunch of switches and a ton of stuff is basically the network. Okay, so it's basically how you can connect all these nodes together so they can exchange data very, very fast. Okay, in scientific computing, it's a fact of life that a lot of data needs to be exchanged. Okay, it's not as if each node can do its calculation for in a couple of minutes without sending any data to anybody else. Typically, every second there's gigabyte of data that needs to be exchanged. So you need a very fast network, and so there's very expensive hardware and software to do that with high bandwidth and very low latency. Okay, and then you have other types of design. So in this class we're going to use this Google Cloud Platform, which is a different type of design. So in this design, in cloud computing, everything is virtual. So you get access to sort of a machine that has some generic characteristics, and when you log on this machine, it may look like it has n number of cores, this amount of memory, and so on, but there is no saying how this is actually realized in hardware. For example, you may request a node with 24 cores, and these cores may be on actually different computers, but it's made to look like just one machine with 24 cores. Okay, so it's a virtual machine, and you have an interface that's sort of it's going to interact in a way that can be quite different from how it's realized in hardware. And then you have the ability to start these nodes, to shut down these nodes, to copy arbitrary files and install arbitrary operating systems. You can have multiple users running on the same hardware, but they don't see each other, okay, like for security reasons and so on. So you're completely sort of isolated. And also the network can be very different. Well, typically, when you are given a group of nodes, they're typically in the same server, but they could actually be in different servers. They could be on the other side of the planet with a network that may, it's not optimized for a very fast network, basically. Okay, so here, this is more like typically a database access or or this sort of thing where you launch a query to a computer. Then there's some reading from a hard drive, do a bit of calculation, returns the result. Okay, that's the typical sort of scenario. So it's quite different from scientific computing, but it serves a lot of applications. But nowadays, cloud computing is pretty advanced, so you can actually have clusters with very fast interconnects, similar to the previous clusters I was talking about. Okay, and then at the very end, you have the sort of top 500 supercomputers, which basically have two purposes. the main purpose is just to impress the guy next door that you have more money and better technology and you're #1 in the world. That's basically what it is. The second is to do some scientific calculation, and the dumber and the bigger, the better. But anyway, so it's a race to who has the biggest computer, and can find some sort of calculation that's semi-useful to occupy this computer. So the biggest, I mean, it's mostly actually for the US, it's mostly nuclear weapons. So it's not nuclear weapons. And though you have applications like, for example, microdynamics or weather prediction that pretty much can consume arbitrary amount of computing. Like microdynamics you can run for months on very large systems, and it can pretty much consume any type of whatever, however big your computer is, you can crank your calculation, So this is the Summit supercomputer. Actually, the name is missing. So it's a Summit supercomputer. So it has some IBM Power 9 processors. So it relies heavily on GPUs. So it has 27,000 NVIDIA GPUs. So the Volta V100s, which is basically the sort of fastest NVIDIA at this point. It has 6 GPUs per node. Okay. So this is actually a very strict requirement. It means that you probably get more flops from the GPUs than from the regular CPU nodes. Okay, so you better use the GPUs, otherwise you're kind of wasting a big chunk of the machine. And using GPUs is very complicated. You need to do a lot of code upgrades and so on. And so how to use efficiently this Volta is actually quite dramatic, quite difficult. So you have 5,000 nodes, 42 teraflop per node. So the top is, I don't know, did I say that? That's not in here. So memory per node, just 500 gigabytes of node. So you have 100 petabytes of memory for the total system. So the interconnect, so this is the network that's being used to connect all the nodes together. So it's this InfiniBand, Mellanox InfiniBand technology. So it's basically a very high-end interconnect. And peak power consumption, 13 megawatts. Okay, so this is definitely a gigantic number. So you need a very special facility to just power this thing. Okay, it's not just putting plugging into the power network, the power grid. That's not sufficient. Okay, so. Okay, so just some more statistics. It's kind of fun to do this every year and see how things change. But so this is the top number 5 right now. So Summit is the one I was just talking about with this NVIDIA Volta V100 processors, 2 million cores, and so on. Next one is Sierra, also the Volta, essentially same type of NVIDIA processor. Okay, just a different location. Lawrence Livermore, the other one is at Oak Ridge. And then you have China, number 3, with the Sunway Taihu Light computer, right? And so actually the top, these are the 3 and 4 are from China. So this is this was a special Sunway processor. This one is Intel Xeon processor. Okay, and the last one is Frontera, which is actually a Dell computer with Xeon processor. That's University of Texas, actually. Right. And then there's another. Actually, this year there was a new sort of list on this top 500 list, which sort of reflects the trends of this time, which is this power consumption, because one of the main limitations going to, for example, exascale is simply that, well, of course you can increase the power and so on, but it becomes extremely expensive. So the main limitation is how to reduce the power consumption of these big machines, like produce more flops for fewer watts. So here, for example, you have the power efficiency, which is the number of gigaflops you can do per watts. And so you can see that actually it's very, very different computers from the previous list. Well, obviously only top 5. Summit is actually right here, so it's actually doing pretty well at 14 gigaflops per watt. Next one here is United States, so 2 different computers. Actually, this one is 24, this one is 373, so these are actually quite low in the list. And then the first 2 actually are very nice computers from Japan. The first one is a Fujitsu computer, and the other one is some other company. So they actually, while the first one is 160 on the list, so it's pretty high. The second one is much lower, so it's much smaller machine, but they're very, very efficient in terms of number of gigaflops per watt that they consume. But you can see that, for example, the power of this guy is 10 megawatt, okay, whereas, for example, this one is 94 kilowatt, and this one is 80 kilowatt, so there's a huge difference in size. But despite the size, Summit they were able to really optimize this. Okay, and so you have also different, this is another plot showing the vendors, some of the main vendors for this technology. So you have Lenovo right here, Huawei, Dell, IBM, different types of IBM here. You have very specialized vendors. You have Cray, NVIDIA. The Sunway is here. This is IBM. We saw that on a couple of machines, so like SGI type machine. And then Bull, which is a European company, I think. All right. And then finally, last plot is the share. So, sorry, it's very small on the screen to fit this diagram here, but this is showing the share of every country. So this is here you have the United States. So here you have China, and then the next one over. I can't read it. Next one over is. On this screen anyways. But the dominant players anyway are United States and China. So obviously China is growing extremely fast. And this was 2010, so this was exactly 10 years ago now. So it was very, very small at that time. And now it dominates with almost a third of all the gigaflops. It basically matches the United States. It's 37%. China is 32%. France is 4%. Okay, so we're somewhere. Japan 6%. The black guy over there, and then the white. Yeah, I can't read this. The font is white on white. Anyway. So it there's definitely used to be dominated by the United States, but now it's much more sort of distributed across the different players. So curiously, like big countries like Russia and so on are not present. Of course, in some sense, Europe is sort of bigger. If you were to merge all the European countries, you get something a little bit bigger. But yeah, Russia at the top is very, very small. The sort of magenta color at the top. Okay, so if you go to top500.org, you can get more info on this. Okay, so I want to give you a little bit of a flavor of what parallel computing is all about. And then just give you this introduction and this little exercise to do, if time allows. So main thing is, parallel programs look very different from sequential programs, okay? And so this comes in 2 ways. First of all, the algorithm itself may be very different, a lot more complicated. So I should write down the algorithm. Then of course, the actual implementation will be different. So then it depends if you use OpenMP, NPI, and so on. So you have CUDA, you have to do OpenCL, OpenACC, and so on. You have to use different languages. So different in many ways, but also in many instances, you may even need to redesign the algorithm completely. For example, in scientific computing, this is very interesting. But as you scale to larger problems, sometimes certain methods, certain calculations themselves become quite slow. For example, fast Fourier transform is very hard to scale. Okay, whereas a fast multiple method which in principle has a lot more flops, is much more efficient in parallel. So there's one thing which is a flop, but then as you scale to bigger and bigger problems, some of the techniques like FFT that are sort of extremely flop efficient, but they require a lot of data exchange, can become extremely slow. And so you have to move from one algorithm to the next. So for example, in the research of one of my students, Leopold, on this hierarchical matrices, one of the steps is the rank revealing QR factorization. And it turns out that if you do a QR factorization, this is a well-known problem, but QR is relatively easy to parallelize, you can do block operations and distributed calculations, very efficient. But when you do rank revealing QR factorization, you need to do column pivoting. Okay, at every step you need to ask, well, what is the next column I should compute with? Okay, and basically until you've chosen that column, you cannot proceed with your calculation. So it's a very, very sequential process, and so that doesn't run well on parallel machines. So now he's scratching his head, how to improve that algorithm, and we haven't really found any good solution, except basically try to shrink how much rank revealing QR we're doing in the algorithm, even if we're doing more flops on, for example, standard QR or other techniques that are easier to parallelize. Okay, but we're trying to shrink the part that essentially is the bottleneck in parallel, and that may mean actually increasing the flops if they're more parallel. So this is sort of semi-interesting, but of course, when you do one sequential calculation, this is what things look like. You do one step, when you're done, you go to the next step, and so on, and everything is just step by step like this, so it's very easy to think about. In parallel, this is more what things look like. So actually, this is something that I'll talk about at the end of the quarter. Well, that's not exactly what a parallel code looks like, because basically the reason why a parallel code doesn't look like this is it's impossible for a human to think in those terms. So, but generally speaking, abstract fashion, this is what a parallel program looks like. So what this is showing is each square is a little bit of calculation, okay, some sort of basic unit of calculation that you declare, is going to be run sequentially. So one core is going to run one of these boxes here, but then each box requires some input data. Okay, so it may be provided by the user, read from a file, and so on, so everything's fine. But typically, it's a result of some other calculation that was done previously. Okay, so then the outgoing arrows are basically data that's produced by this calculation and that is required by some other box somewhere else. Okay, so you have all these basic, groups of calculations, and with incoming arrows, that's the data they need, and outgoing arrows, this is the data they're producing and going to be consumed by somebody else. So this is called task-based parallel computing. So everything is broken down in tasks with these dependencies, and you have special frameworks and languages that allow you to write your code in this fashion, and essentially then the library or whatever the system you're using is going to look at all the tasks, all their dependencies, and then figure out a way to optimally or as best as possible schedule this in parallel on the computer. It's going to start maybe from the left here, and then as soon as computer computation is finished, releases some data, then you can start some other kernel and so on, and there's a system to manage this. So in practice, of course, this is very hard to think about, and this is why we have these special parallel task-based environments to help you do that. So what we're going to see is something that looks a little bit like this, but much simplified, but they're also therefore less efficient. Okay, so we're going to look at sort of NPI or OpenMP, which are sort of simpler versions of this. And as a result, they are less efficient, and so that's why that this going to this task-based and making things completely asynchronous is sort of the more the state of the art in parallel computing. So let's look at this this problem. Let's let's assume that there is some calculation, some expensive calculation that takes many flops, and then we get this result x, and we want to sum up all these results. So I could have put I as argument of compute next value, but okay, doesn't matter. So you call this function, do some operation and do the additions. So let's say that we have P cores, and you want to use P cores to do this calculation. Okay? So going back here, the basic problem is you have plus equal. Okay? So when you do plus equal, it's a seemingly very simple operation, but you need to grab the current value, add something to it, and then write back to memory the new value. So in principle, this is a sequential process. Like you grab the value while you're doing your operation. Nobody else can change the variable, and once you're done writing, then somebody else can grab it, do its operation, and you keep going. So if you think naively, this is a completely sequential process, and you cannot parallelize this. So obviously, this is not the case. This can be parallelized, but it's not entirely straightforward how to do it. Okay. So you want to split the work amongst the different cores. So here is the basic, strategy. Okay, so the basic strategy is to say, well, okay, it is true that when you do this plus equal, this is inherently a sequential operation. There's no denying that. But what I'm going to do is I'm going to have each of my cores or computing units just sum up a chunk of the data. So let me write up on this board here, visually. So we see what's going on. So basically, you can imagine the input simply as a box, okay, where I say this is I equals 0, and this is the end of your array. And so, these are all the x values. I mean, there's no array, but this is just sort of a way to think about this. So you're going to split your input like this, okay, into chunks, say 4 chunks here, and then you're going to have a core, then grab a chunk here, and do the addition. So essentially, you're using the fact that the addition, is associative, right, or even commutative. That is, you can do this addition here, you can do this addition here, here, and here independently, and then bring all these results together and do one final addition, and you have the result. Okay? So when you want to add a whole bunch of numbers, you can definitely break that down in groups, do the addition in each group, and then once you have all the partial results, do a final addition. So this is what's happening here. So all the cores are going to sum up B numbers. So it's a little bit of a simplified setup. I'm assuming that I can split the input into chunks of size exactly B. Okay, so each process is going to sum up a chunk of size B. So R is my thread number. So it's each worker, and this is also a very common sort of way to proceed in scientific computing, that each core is assigned a number. So you sort of know what you're supposed to be doing in this calculation, like where you're at. So in this case here, R is simply the block number, like which chunk you're supposed to be summing up. So then my first I and my last I is basically the beginning and end index for the chunk that you're supposed to be working on. And then, okay, you just go. Okay, start from the first index, and here, do your calculation, and so on. So now my sum is each core is going to have its own copy of my sum. Okay, this is not the final result I'm after. These are just partial sums that happen for each chunk here. And now I need to take all these sums and do a final addition. Okay, so everybody follow so far? Okay, so basically this is how you do it. Right. So so each core has computed a partial sum, and now you've got to take all these partial sums and sum them together. So for example, if you have 4 cores, you're going to end up with 4 partial sums, 4 numbers that need to be added together. So the numbers you end up with is basically equal to the number of computing units, and they need to be added up together. So the easiest is, so again, adding up these numbers together. Again, this is another sequential operation. How should you do that? Well, the easiest is just say, well, one of the cores, which I'm going to call the master, okay, so again, convention in parallel computing, is going to grab all these numbers, just add them together, and produce the final result. So you're going to say core 0, for example, with this arbitrary numbering, is going to grab all these values. So maybe it has its own my sum. It's going to grab the my sum from all the other cores. Okay, so 3 additional values, sum all these guys together, and do the plus. So now this is a sequential process, right? Everybody needs to send core 0 its value, and then core 0 needs to add up. So the cost is basically proportional to the number of cores. Okay, and of course the time it takes to send the data and the time it takes to add, but it's proportional to, the running time is proportional to number of cores. So this is what this may look like. So there are many styles of parallel computing. So actually this is the style that we're really going to cover at the end of the quarter, okay, with MPI, okay, with send message. And so the way the code is written here, is you can see how immediately this becomes a lot more complicated, okay? The idea is you want to write one piece of code, and you don't make a difference, like everybody's running the same code, okay? It's not as if for each core, like core number, I, you're going to create a special program just for core number I. That might be possible, but it sounds very complicated, so this is not how people do it. What you do is you have one program that everybody runs, because everybody's running the same program, but each core does something different because it has a different core ID, okay? So at some point in your code, you have to say, well, if your core 0 or if your core 1, then do this or do that, and so on and so forth, and this is how everybody does something that's kind of useful. Okay, so here in this code, everybody's doing this, and so depending on whether you core 0 or you're somebody else, then you've got to do something different. Okay, so the core 0 essentially is going to be waiting for everybody else to send that data over. Okay, and then once everybody has sent the data, then core 0 is going to do the sum. All the other guys are simply going to do a send. Okay, so here, for example, this is what happens on the student memory, where you need to send the data across the network. So you need an actual explicit instruction like send and receive and so on for this data exchange. So we're going to start with OpenMP, which is a lot simpler, shared memory. So you can read and write to the same memory, so there's no send and receive. But conceptually, it's still very, very close to this model. Okay, so all the worker threads, they're done computing my sum, and they're going to send this result to process 0. So this is just pseudocode, right? This is not an actual working code, but this is just to kind of illustrate the ideas. And then the master thread is then going to loop over all the other guys and just waiting for core 1 to send its data. Okay, once it has the data, then it goes waiting for core 2 to send the data, and then core 3 to send the data, and so on. So it's just looping over all the other cores, waiting for everybody to send the data. Okay, so the data is coming from core, RO. Okay, and then you store the result here, and then you add this partial result to sum. Okay, and so at the end of this loop, sum has the final sum. So you can see immediately, just by staring at this code, that the running time of this is proportional to the number of cores that you have. Okay. Okay. So now, if you think about this algorithm, and you're trying to figure out, what the performance of this is, or how well this is going to work, then how would you analyze this code? Like, how would you model the performance or the running time of this code? Okay, so the way to think about that is to look at, well, what are the flops? What am I trying to do here? Okay, I'm trying to, so let's go back. I'm trying to run this function, and then I'm trying to do an addition. Okay, so you can calculate how long it takes to do an addition, and how long it takes to run this function. Okay, so hopefully there's a lot of flops in here. So it's going to take a certain amount of time. Okay, you divide this time by p. That is the optimal you can do. Right? You cannot be faster than this. Okay, once you reach that number, then everything is sort of perfect. So if you look at how this code is written, then first you run through that, and that in some sense is the minimum amount of time because everybody's just running completely in parallel compute and doing the addition. Okay, so once you're done here, this is sort of the absolute minimum you can do. Okay, and then the next piece here is basically, sort of the overhead, you could say, of running in parallel. Okay, this is extra work. Like you have to send data across the network, and you have to do this final addition sequentially. So the time you spend here is sort of the overhead of running in parallel. Okay, it's the part that's inefficient. So now if you look at this, how can you determine whether this is going to be efficient or not? Like, what are the key sort of parameters? Yeah.
Well, you want to see that the serial part isn't taking longer than the parallel part, because otherwise.
Right. Exactly. Okay. And going one step further, it depends how long it takes to do this compute next value. Okay. And essentially, right, the point I'm getting at is the time it takes to run this depends on this times the size of the chunk. Okay. And the time it takes to run this depends on the number of cores. Okay. And so you see that there's something that eventually this thing has to break as you increase the number of cores. Why is that? Because as you increase the number of cores, well, that part here just increases like p. Okay? But then the chunk size is basically n divided by p. So it becomes smaller and smaller. Okay? And even if compute next value is relatively expensive, the send receive is typically super slow. Okay? So it means that you need very, very big chunks, either that or you need a compute next value that really has a lot of flops. Okay? And so these are important trade-offs to understand, the performance of this algorithm. Okay, so this is number one. But as you increase, the number of cores and the limit of p equal n, then typically this is going to be very inefficient. Okay, it's going to the performance improvement will sort of go down. All right, so that seems okay, but there are many, for example, if you go to a GPU, there are many cases where, in fact, this compute next value is completely trivial. For example, let's say you calculate the L2 norm of a vector. Okay, you calculate the L2 norm of a vector, so you're just summing up, for example, xi squared. Okay, so the compute next value would be take xi, take the square, and then you have to do the sum. So it's actually completely trivial. There's hardly any flops. Okay. Now p, the number of cores, could be gigantic. It could be in the thousands. All right. And so let's say, for example, you take a vector of size 10,000, and you have 1,000 cores. Then each core is going to do 10 flops, whereas this worker 0 is going to have to do 1,000 flops. So actually, although it looks good on paper, there's a big problem with this plus equal. I mean, this does not, of course, happen in all cases. This is the case, for example, for GPUs, but in many other calculations, the chunk size might be gigantic, and so this may be a very reasonable approach. Okay, but for example, on GPUs, that typically is not going to work because you just have too many threads that are computing super fast, and if you just send to thread 0, then it will take forever to just add those numbers. Okay, like the first part of the calculation will go super fast, and this one will take forever. Okay, so this is something that, I've shrunk the class, so I typically talk about this algorithm. Maybe not so much this year, but typically the guys in NVIDIA talk about this. So you will hear about this later. But the way to correctly do that is, first of all, there is always a limit to scaling. So this second phase, where the master is adding all the numbers, so in the current implementation, the running time is p. Okay, so that's very bad. Okay, the best you can do is log p. So it means that if you keep pushing things, if you keep increasing p, again it becomes inefficient. But log p, that's a lot better than p. So typically, it will be sufficient for most applications. And so the way this works is that, essentially you have p numbers to add, and you're going to be using at every step as many processes as possible to do this summation. So when you start, you're going to take essentially each core is going to add just 2 numbers, right? So if you start with p numbers and p cores, and each core add 2 numbers, half of the cores are idle, but there's nothing you can do there. Okay. So this is essentially the first stage, where each core adds just 2 numbers, and then the cores like from 8 to 15 are just idle. And then the next stage, again, each core takes 2 numbers, add them, so now you again divide number of cores by 2 and so on. So you have fewer and fewer cores, and you can see that in this algorithm, actually what matters is not the number of flops you're doing, okay, because in fact, a lot of the cores are idle, so if you had more flops, there would be no problem doing more flops. What matters is the so-called number of passes. So because of the dependencies, you cannot start this step until you're done with the step before. Okay? And so the number of passes here that you're doing is log p. Okay, so in log p passes, you're going to be able to compute your result. Okay. So hence the running time is the cost of compute next value and adding up all the chunks here. So this is a completely parallel phase, and then plus log p times essentially the cost of doing this addition. So log p typically is quite reasonable, and that will go quite fast. Okay. But so you see that so this is a very classical and important algorithm in GPU computing, because you have a very, very large number of cores, and they all compute like super fast. So you need this type of strategy and many similar strategies to get good performance on a GPU. So this shows you how this can be quite complicated. And so if you go to linear algebra problems like LU factorization or matrix multiplication or QR and so on, this has been going on for 30 years, and people are still cranking out papers on this topic because it's just such a rich and complicated question. Okay, so basically, purpose of the class. So here we're not going to look too much at algorithms, just kind of a little bit, because of course the languages can reflect the reality of the hardware and sort of the bottlenecks that you have in most calculations. So we're just going to look at algorithms as just illustrations, so to illustrate difficulties and bottlenecks that may appear in your calculation, but the focus really is on learning the parallel languages. So in that sense, it's relatively straightforward. Actually, the most difficult part would be the part on GPU computing, because there we'll talk really about performance, how to optimize your algorithm, understanding the algorithm and the hardware, and changing the algorithm so that it better matches the hardware. So this will be the more difficult part of the class. Okay, so I guess my demo will definitely be postponed to next lecture. So I'm just going to talk about first shared memory processor. This is going to be essentially the first maybe third of third of this quarter. Then moving to GPU computing, which actually falls under shared memory. So maybe it's a bit more than that. And then the end of the quarter will be distributed memory computing. So shared memory. So I talked about this. And so this is the simplest architecture, and so if you have a shared memory computer, these are the simplest to program. Okay, so very so not that simple, but the simplest. So you assume, so basically here is the model. So the hardware could be a lot more complicated, but at least the mental model is relatively simple. So you have a number of processors. So actually. So they can be called processors or cores, same thing. And then there's a shared physical memory, okay? And by shared, we mean that every process can simply read and write to memory, okay? Like the usual C++ code and so on, allocating memory and accessing memory and so on. And so it's shared, so everybody can read and write to the same memory. And to a large extent, the performance of accessing any memory location is roughly constant. Okay. And so now, of course, in practice, the cores are always separate from the memory, right? They're physically separate. So in between there's some sort of interconnect. Okay, and so depending here on what this network looks like, so this network is just on the motherboard, but it's still a network. Okay, just sitting on the motherboard, so inside your computer, inside your laptop, if you open it up. But so there's a network, and so depending on the structure of this network, you may get slightly different things. So this is the basic. So this is the simplest, again, shared memory. So here you assume that. So again, you have the processors. So they all have their own cache. Okay, so typically the cache. We look later on at an example of architecture. So they can be either completely local to a core, or maybe they can be shared by a few cores and so on. So there are different ways of doing this, but typically it's something quite local, very, very close to computing units, to the floating point units, okay? Because it's close, it's also small. So it's very fast, but it's very small. Okay, the closer you are, the smaller you have to be, but you're also very, very fast because of the physical distance is just very small. Okay, and then you have memory. So here in this model, you assume that memory is just a separate thing. Okay, and in between there is an interconnection network. So here in this model, essentially each time a processor makes a request to memory, it goes to this network, and it sort of doesn't matter where the data actually is in this memory. Okay, the read and write time is roughly the same. Okay, so everything is sort of flat. You can read and write anywhere in memory with about the same speed. Okay, so this is the simplest sort of model. So now in practice, especially if you go to sort of high-end scientific clusters and so on, where you really have a lot of sockets, so each socket has a processor, and there's a lot of memory, so everything becomes even more distributed, right? You have many memory DIMMs and so on, different places. And so, it's very, very hard to get essentially the high performance to any point in memory. Okay, you just need too many wires, basically. It's very, very difficult. So it's basically just a problem of locality. You need to be fast if you're close to memory, but not everybody can be close to memory, right? That's why Palo Alto, housing is so expensive in Palo Alto, not everybody can be in Palo Alto, right? It's just no space. Okay. So, all right. So that's why the guys like me, they have to commute. Far away. All right. So, so NUMA means that there is some part of the memory that's going to be close to a processor, and then other parts of the memory that are farther away. So this is much trickier because as a programmer, when you write shared memory, it looks like this is just one big memory. I mean, you don't know where things are. Okay, and so we'll talk a little bit about that later on, maybe. This gets more complicated. But what matters is that in terms of performance, you will see big differences that may actually be hard to explain. Because depending on where the data is, if it's close, your program is going to run very fast. If the processor starts accessing memory that's farther away, then the performance will dip significantly. Okay, so it makes writing programs a lot more difficult and interpreting performance a lot more difficult. Okay, so I guess I'm going to finish around that. So it's called NUMA, non-uniform memory access. Again, this is kind of what this looks like now. So now, if this looks like, well, it's sort of close to the previous diagram. But what this means is that basically, as a core, it's like, okay, this is some famous professor at Stanford. Okay, his home is in Palo Alto. Okay, so it's his own home and so on. Okay, so this is me, also work at Stanford, but lives different place. So this famous professor wants to, come and have dinner at my house. Gotta travel. Okay, and so it means that each core is sort of designed with special access to, a memory that's very close. But if you want to access some other memory, there's a different route through a network. Okay, so it's much slower. So again, this can be arbitrarily complicated. So this is just sort of a mental model. And so I will not talk too much about that because it's complicated and again the focus is more on learning languages. But this has a huge impact on performance and interpreting performance of multi-core programs. And it means that also interpreting performance and optimizing your code is very difficult because of all this complexity here. So here is, for example, so I just want to finish this topic before wrapping up. So here is, for example, the schematic of essentially the topology of a processor. So it's a bulldozer, so it's an MD series of so it's actually multiple processors. So here on the left, you have one socket. Here on the right, you have another socket, okay? And this is a processor here, okay? This processor has actually 8 cores. So each one of these boxes here is 1 core. Okay, so let's say these 2 cores. So they each have, L1 data. They share L1 instruction. They share L2. Okay, and then these 8 guys share an L3 cache. Okay, right across here. Okay, and then here you have the memory of this NUMA node. Okay, so it's 8 gigabyte in this case. Okay, the number is very small, but it's 8 gigabyte. So it means that this guy accesses his data extremely fast, a little bit slower, and even slower. Okay, and so this is sort of one box that was highly optimized. Okay, but now they want to pack more computing on this computer. So what they did on the motherboard, they have 4 of these guys together. Okay, and with some network connecting them. So now, if there is a variable that is stored here, needs to be accessed by this core, then this has to go over the network. Okay, it's going to be much slower. Okay, so there's this type of effect here. So this is, for example, showing you just very briefly, like a GPU socket, a bunch of memory slots all over the place. So they try to be close, but you can see that not everybody can be close to all the sockets, PCI Express and so on. So just time to kind of wrap up. Okay, so I just want to maybe just just finish with these last 2 slides. So this is just sort of, again, I'm not going to go too much into that, but this is just giving you this idea that you have the different levels of cache with registers, the fastest, then L1, L2, L3, and essentially, the further down you are, the more space you have, but the slower, the farther away you are, so the slower, the longer it takes to get the data. Okay. And so here you have another table, but I'm going to skip that with just some numbers. These are the size. For example, L1 cache, 32 kilobyte, L2 cache, 256. Main memory, 4 gigabytes, and so on. Then you have I/O and hard drives, 6 terabytes. Then you have the latency. So latency is the time it takes to just get one piece of data, because there's sort of a warm-up time, so to speak, right? If you request data, it doesn't come immediately. There's a latency, so it's sort of minimum time to send any type of data. And bandwidth is a different concept. Bandwidth is if you request a lot of data, then this sort of warm-up time is relevant. So things start, coming in, and then once you reach peak transfer rate, then what is the rate of transfer? This is the bandwidth. Okay, so this is when you're fully utilizing your wires. So you're done with this sort of warm-up time. You've reached the peak transfer rate, and so this is the bandwidth. And so L1, for example, 1 terabyte per second. So it's huge, but it has to match the compute rate of the processor. And then the L3 cache is, for example, 400 gigabyte. The main memory is 100 gigabyte. And then the hard drives might be 25 gigabyte per second, which is actually quite high. Okay, so I guess I stop here. So, time to wrap up. So Friday we'll have the C++ refresher. So the class on Friday. And then, so we skip Monday next week, and then Wednesday, so I'll continue this lecture. So if you can bring your computer for Wednesday next week, as well. Actually, obviously, you need it for Friday, I guess, right? William? Yeah, for Friday, they need their computers. Yeah, you're right. So yeah, you can bring your computers for Friday, and then Wednesday, but generally speaking, I think it's good to have your computer so that I can just do, exercise and so on if time allows. Okay, thank you.